Alright, so let us extend our previous talk, and here we talk about capacitive feed through. And then we also talk about the parasitics. So they can be a capacitance, they can be a resistance which occur due to the structural fabrication of a mechanical transducer. And then we'll discuss about the electrical equivalent circuit. So we'll derive this equivalent circuit from a mechanical domain to the electrical domain. So we'll see that how MEMS transducer, which is inherently mechanical in nature, has a representation in the electrical domain by means of an electrical equivalent circuit. So let us understand how the structural fabrication of a simple mechanical transducer is made. So for example, you start with the silicon substrate over here, and then on top of that you grow an oxide. So let us say this is an oxide layer over here, okay, and on top of that then we grow because of the photolithography and some other etching steps. We deposit a metal over here, so which acts as an electrode to actuate the transducer, and then this area is etched away. Then again the photolithography cycle comes, and then we can have deposition of the structural layer. So it looks like similar to this. So this is basically a beam that we can see that which is deposited, and this portion right over here, that is etched away with some etching steps. So what we understand here is this is a beam of a vibrating structure or which is clamped over here, and then this is your silicon, that is oxide. So it's usually SiO2, and then we have this polysilicon, so, or it could be a metal, and then there is again a poly. So in the typical CMOS process, we have a different layer which is poly 1, poly 2, SiO2, silicon nitride, etc. So let's say this is poly 1 and this is poly 2, where poly 1 is used to act as a bottom electrode, and the poly 2, it's acting as a structural layer or a structure of a vibrating element. So let us understand where are the feed through capacitance. So you have this actuation electrode over here, there is drive electrode, and then there is this capacitance which is C0, which is inherent in the structure. And in the last talk we've seen that we are going to bias this vibrating element with the polarization voltage Vp as a resistor, and we are going to sense from the same structure itself. So you have this capacitor to block this DC voltage, and here what you have is output current, which is total current. So total current is basically, we've seen that is due to feed through, which is IF, and another component of this current is IM, which is due to motion. So when you have a VDC or VP, polarization voltage, and VI, that exerts an attractive electrostatic force across this capacitive gap, which will put this beam into vibration. And so because of that motion we have this component Im. However, we also have this input to output. So this is input of our transducer, and that is an output of our transducer right over here. So there is again a signal path from input via this capacitor to this over here. So that is a feed through component over here. As we can see that this is IF. So the current due to current through this capacitance which is there. So C naught, we know that is epsilon A over D. So epsilon A, epsilon is the permittivity, and A is the cross section area. So over here this bottom electrode area and the area of this beam, which is overlapping area, and D is the gap between these two parallel plate capacitors. So now we have this structure. We've seen that. Now where are the parasitics? Parasitics in the sense we have this capacitance, we have a resistance. Obviously this is a substrate, so we have the resistance because it is n-type or p-type substrate. Because of the doping we have this resistance over here. Now you have this polysilicon, this top layer, then you have this SiO2 which is an oxide, and then you have a silicon. So there is this capacitance as well. Alright, so this capacitance is there right over here, but we have to see that and there is this capacitance as well over here, but we have to see that we are actuating by this electrode right over here in the middle, and on top of it we have this beam. So from input to output, are there any parasitics related with that? So we see that this is a poly layer, or say a metal, then this is an oxide, and then this is a substrate. So we have this capacitance over here. So let's say this is called as C pad. All right, so we can see that this capacitance comes into picture, and then we also have this capacitance over here. This is also C pad, because we are sensing the output from this particular node. So we can see that this equivalent circuit of this mechanical transducer can be represented by RLC equivalent network. So how to derive this equivalent circuit? First of all, we have to understand what is the mapping between a mechanical domain and then to the electrical domain. Alright, so in a mechanical domain, a force F, which is a drive force we are using, or any mechanical force, that can be represented by a voltage V in the electrical domain. We have a velocity which is x dot in the mechanical. It's like when the beam starts vibrating, it has a velocity indicated by x dot. So an electrical domain, that is a current that is represented by I. Then a derivative of displacement dx dt is a velocity. So the displacement here is indicated by x, and that is equivalent charge in the in the electrical domain. Similarly, we've seen that what is the spring constant of this, because we have this structure can be represented by a simple mass spring, 1 degree of mass spring damper system. So you have mass over here, then you have a spring, then you have a damper, and that is suspended to a frame, and because of the actuation force we have a displacement of this proof mass, and hence the velocity, etc. So what we understand that we have this spring over here that is indicated by K, so it can be represented by 1 over C in the electrical domain. Okay, uh, so that is a capacitance. Or inversely we can also write that we take the reciprocal of the spring, we take the reciprocal of the spring 1 over K, and that will represent by the capacitance C. Capacitance C. C. All right. Finally, this mass, proof mass M, is represented by inductance L, and we have a damping, so that is indicated by B. That damping coefficient is indicated by a resistance R in the electrical domain. So how do we derive now? So now we have a mechanical transducer, mass, spring, and the damper, and we know that so it can be represented by simple resistance R, which is a damping associated with this structure over here, this structure, and then we have the proof mass, which is the vibrating beam, is indicated by L, and then we have this capacitance which is a reciprocal of this spring. Okay, so 1 over K. So that is a equivalent circuit, but now we have to apply the force. We apply the force by the combination of applied voltages VI and VP to the mechanical structure. In the electrical domain, we can apply the voltage again here, so we can say that that is voltage V. Okay, and then we have this so this is an input port of your electrical circuit, and that is an output port of an electrical circuit. Okay, so output, what is an output? Output is I of T, which is the total current, and it is a combination of IF and IM. So this will give me the component IM, which is due to motion of the vibrating element, whereas I can have the input to output feed through as demonstrated by this line earlier. I can have this input to output, so this is C feed through, let us say C feed through, and this is basically C naught, so let us say we'll call it C naught. So this is this capacitance which is inherently there. Now from the bottom electrode right over here, I'm applying this and there is this capacitance, so it's between poly 1 oxide and the silicon substrate. So this capacitance is at the input port, so I can draw a capacitance over here. So this is a parasitic and I call it as a C pad, because I'm going to probe or apply voltage at this electrode, so it's going to have the C pad. Is there any output parasitic at the output node right over here? So let us see, we are sensing the current over here, so from this this structure over here. So is there any capacitance associated with that? Yes, because on beneath this metal or polysilicon top layer there is an oxide and there is a substrate. So I also have this capacitance over here, so I will call it as a C pad. So these are the intrinsic parasitics associated with this structure, and this is an equivalent circuit. So this is an equivalent circuit of the mechanical transducer. All right, transducer. So here is how the complete circuitry goes, and we've seen that how to transform between the two domains, that is mechanical to the electrical domain. So let us fabricate a different structure and see various parasitics and feed through, and based on that try to draw an equivalent circuit. So for example, I start with the silicon substrate over here, and then I have the oxide layer. So I'm going to have an oxide layer over here. So this is an oxide layer, so it's basically an oxide or SiO2. And then through photolithography and the etching process, I managed to fabricate these electrodes. So let us say this is electrode 1, and that is an electrode 2. Over here, and then on top of it, as per the fabrication rule, I have the structure on top of it. So let's say this is a beam, and this of course, so these are the poly 1, let's say, or metal 1, and this is poly 2 or metal 2. So these are the electrodes and the main body of a vibrating element. Where are the capacitances? So let's say I decide to drive this structure from this electrode. So I have an application of Vi of t. All right, and then I have this I apply the polarization voltage through this resistor to limit the current, and I have this voltage over here. So this Vi and Vp will exert an electrostatic force, which is an attractive across this capacitive gap. So there is this capacitive gap over here. So let us draw it properly. So here is this capacitance. So let's say this is C1, and there is another capacitive gap right here, and this capacitance, let's say C2. Across this capacitive gap I'm gonna sense the signal. So right from here I have I of t, okay, which is a combination of IF plus IM, where IF is the component of current due to feed through and IM is the component of current due to motion of this vibrating element. Uh, okay, so I am sensing this is an input, this is an output. So how to have the feed through path? So feed through path is going to be like this. I have this one and then through this one I have this one. So obviously these two capacitances are in series, so effective capacitance, let's say C1 and C2 are equal, so the effective capacitance is C over 2. So this is called as two-port combination, two-port mechanical transducer, as compared to the previous, which was one-port uh, transducer. So in two-port, the component due to the feed through it's reduced, because this IF, which is given by j omega c into applied voltage, which is the admittance of this capacitance, and C gets reduced in the two-port combination. So therefore the impact of feed through can be mitigated or reduced to a certain level over here. Okay, so we've seen that in the previous talk. So now where are the parasitics associated over here? So we've seen that this is your one layer, this is an oxide and this is a substrate. So there is this capacitance over here, okay, because at the input node, and at the output node we also have this electrode, and there is this oxide, and then there is this uh, there is this silicon. So we have this capacitance right over here, okay. So this is C pad, because we are sensing the output from here, and this is we are sensing the, we are applying the signal at this port, so it is also C pad. So when we are trying to draw the equivalent circuit, it would be simply resistance, as we've seen before, and then we have this inductance, and then we have this capacitance. So these are the components, they are coming due to the motion. The current through them is due to the motion, let's say Im. And then you have this input port, and then we have this applied voltage over here. However, there is this capacitance which we've derived with respect to ground, C pad, at the input node, and then there is an output node, C pad again, so at the output. So this is an input, this is an input, and that is an output over here. So where is the feed through now? The current due to feed through is right over here, and this capacitance is C by 2. So obviously the current through this capacitance is reduced, okay. So you have this IF, and then total current is IT. I of t will be IF plus IM, okay. And then if you have the load RL, so this I of t flows through RL, and what we have is the output voltage VO of t, which is I of t into RL. So that is how this structure is formed, and the equivalent circuit is formed. What if we have to amplify the current due to uh, due to uh, uh, due to this transaction? So what we can do here is, for example, so let's say you have this uh, current over here, which is a total current, and then that motion current is given to an amplifier. So for example, it could be a current to voltage converter, where you have this amplifier and then you have this voltage over here, VO of t. Okay, so that voltage can be sensed across the output load, let's say RL, and this VM V of t will be is basically I of t into the RF feedback resistance of this, or say the trans impedance gain of this amplifier. Okay, so this is how we can derive this equivalent circuit parasitics associated with that, and so that's all.